This conference will now be recorded.
Okay, today we're going to take a little detour away from what's known as the time domain and spend some time in the frequency domain. Let's see here. So we're going to talk a little bit about what do I mean by frequency domain as opposed to this. Then we'll spend some time talking about Fourier transforms and Fourier series. That's something we just kind of hinted at a little bit in class because we'll use them for covariates in some other models. Then I'll talk just a little bit more generally about spectral analysis, of which Fourier and Fourier analysis and transforms are part of, and then we'll end with some examples about wavelets. Okay, so far, like I said, we've really been focusing on time series analysis in the time domain. That means essentially we think about data like this, where we have the y, here is some amplitude or displacement, x, and then the x-axis here is time. And so, we're really thinking about how things are moving up and down as we move through time, but in the frequency domain, we're really going to think about how things are moving up and down, not with respect to time, but with respect to frequency. And that can be a little bit hard to wrap your head around initially, but we'll have some examples to sort of demonstrate what that is. So to motivate this, we should probably introduce a rather famous mathematician and physicist from the late 1700s, early 1800s, Jean-Baptiste Fourier, who spent a lot of time working on heat equations, and vibrational aspects. He was interested in how vibrations cause heat and how heat transferred from subject to subject. And it's actually not particularly well known, but he is, in essence, credited with discovering the greenhouse effect. And that is because as he was doing these heat measurements, he had essentially drawn up on a chalkboard a model of the sun and the earth, and did some calculations and figured out that the earth was, or should be, cooler than it really was, because they had a number of actual temperature measurements during the time. And so he figured out that the way that must be is that as the sun's rays were penetrating the atmosphere itself must act like a bit of a cloak, and it was heating. And he based this on some experiments that somebody else did, where they took some vases, some flower vases, and they painted parts of them black by lining them with some like burnt cork. And so they were able to shade some of these things and measure the temperature in there. They didn't control for advection, but it was the 1700s. So anyway, it was pretty cool nonetheless. But the issue that Fourier was wrestling with was that the equations that sort of govern the laws of heat mechanics are all partial differential equations, and solving those analytically is very often impossible, and so you have to do so numerically. And he didn't have the benefit of microcomputers or maxi computers or whatever the case may be. So he had to figure out a way to make the solutions to very hard problems easier. So he got to thinking about this a little more, and what he did was posit that, well, we have this sort of situation where we have a really hard problem, but if I could transform the problem into something that was much easier to solve, and then figure out a transformation from the transformed solution back, that would be a lot easier than trying to mess with this arrow right here. So what he did was describe a number of Fourier transforms and inverse Fourier transforms that allow you to do this. So it turns out that working in this space with these types of problems is way easier than it is in normal space over here. So this led to some work where he described what he later called after him Fourier series, which means that you can describe some complex, typically periodic signal through time now as an infinite sum of sine waves. And if you allow for different numbers of waves, that's this index k, and you allow them to have different amplitudes and different phases, then you can think of having a whole bunch of springs that you stretch or pull or just shift one way or the other this way. And if you stack a whole bunch on top of those things, sure enough, you can make something that will look quite periodic and may look very bizarre. So here's a finite example now of one that I simulated. So here I'm taking 5 waves. Okay, it's going to go from 1 to 5. The weights here are just 1 over k, and the phase shift is just k squared. So the colored lines back here are the 5 different sine waves, and the black wave is the sum of all those. So if we had a signal that looked like this, we could in fact describe that with 5 different sine waves. And you can imagine that, yeah, if we stacked up 7 or 9 or a dozen, we could probably come up with lots of different interesting things. And if we took away all but one, and we just had this one long sinusoidal pattern, that would actually do pretty well with some things like air temperature in North America or something like that, right? Where we have these very strong seasons, like, or day length, okay? If you then think about now, there are 5 different time series in the background here. Each one of them has some amplitude. If we take this picture and stretch it, pull it out of the board, and then look down the sine waves, we can look at how tall they are, the amplitude. So that's what I've done here. So this was wave 1, 2, 3, 4, and I've just ordered them such that this one has relatively small amplitude and the first one has relatively large amplitude. And I found this example on Wikipedia that is super cool, and this person has way more skills than I do. So here's a wave. The red wave is a composite of the blue. And here in this case, they mix sine and cosine waves, but you can recover this by just mixing others. So here's now they're going to stretch those different waves out and turn this around and look. So this is now the amplitude as a function of the frequencies. So that's all, in essence, for a Fourier series is and a Fourier representation of it. And if you know the mapping, if you know how you got from here to here, there's an inverse mapping to take you back so you can recover the actual original series. Okay. Okay. So that's a Fourier series. Now we need to think about this transform. So the way Fourier did this was he made use of Euler's formula, which I know everybody remembers really well, which is the mix of a sine and a cosine wave, where one of these has an imaginary piece, can be expressed as an exponential with an imaginary piece in the exponent. And engineers work in this type of systems all the time. So a Fourier transform then is just some integral from minus infinity to infinity of this inverse transform times e to some power here, where the power is a function of time and the sort of number of different waves. Here's our transform in discrete space right here. So now we've got, this is our x, here's our Fourier transform, here's this exponent e to the minus 2 pi, n is just the number of waves we're allowing for, and k is the actual frequency. And to do this in R, it's really simple. There's a function called FT, which stands for fast Fourier transform. You just pass it a vector of numbers, and it will spit out the resulting Fourier transform. The length of FT is going to be the length of XT. So for every one of those time points, it's going to estimate the influence of the different number of frequencies. So what's typically done then is people will normalize this by the length of this just to shrink these values to a unit scale. The reason this is called fast Fourier transform is that in the estimation of this, in order to be exhaustive, you have to search over n squared different combinations of your x's here. And in the fast form, it's n times like n log, or n times log n. So it cuts down on the sample space that it has to deal with. So it's not perfect, but for a lot of problems that you work with, the fast system is really easy, and that's what R settles on. So it's quick. I mean, it will do this more or less instantly. You just pretty much hit the enter key and you have the answer. So this, when I pass the original time series, so I execute these commands here where xt is that original kind of stacked sine waves that I showed you. This is the Fourier representation it comes up with. So here's the frequencies, and it thinks they're at 2, 4, 6, 8, and 10. When you remember, all we did was add actually 1, 2, 3, 4, and 5. So somewhere now here, it's got the amplitude a little bit mixed, and it's kind of zeroing out these intermediate ones. There's a little bit of influence here, and once you get out here, it's just nothing. So, okay, we have a relatively short time series. I didn't make it particularly long. If we want to then see if we can recover that from it. So here's our Fourier transform, where the x's are on the inside here, and we have e to the minus quantity. The inverse is just that these two trade places, we're going to index over k, and this minus sign goes away. So if you have these estimated Fourier transforms, to go back to the x's means you're just going to multiply those times this quantity here. And you can do that really easily in R, right? You just create a definition of an imaginary number, and in R there isn't a real good way to do that other than this command complex, which says give me one complex number. I want the real part to be 0 and the imaginary part to be 1. So that is just I. Create an empty time series, create a sequence now where they like to index from 0 up to n minus 1, and then just do this summation. So this function, or this command down here, is just exactly the same thing that I showed you right here. It's just this formula. Okay, so if we do that, and then we pass that to R and plot it, the dashed blue line here is overlaid on top of our original series. So even though it didn't get the exact frequencies right, the mixture that it picked was close enough that, of course, the inverse here manages to recover exactly. This isn't too surprising because that's a very deterministic signal that we passed it, right? There wasn't a lot of noise around it. So this is a good spot to talk about where you see these kinds of work in practice. Who works in the frequency domain? Well, engineers do, in the medical profession, anything where you think about like electrical impulses. So think about like an EKG or an EEG, these types of things. So they look at some sort of displacement, time in between things, right? If you have a pulse, boom, boom. They want to know how high the activation energy is. They want to know how far apart the spikes are and that sort of time. So that's a thing we're thinking about in cycles, hertz, beats per minute, these types of things. If you're lazy and not a good typist, you can actually recover the inverse by just passing this argument inverse equals true to FFT, and you don't have to write that little loop and that other code to produce the inverse. It will just do it for you. And if you do that and plot that, you get the exact same answer as we did before. So we did it the same way that R did it, and both of them look to be right. That's good. Okay. Any questions specifically on Fourier analysis or Fourier transform? I should say that you can take like a whole course on this. And the wavelets we'll talk about at the end. I took a full 3-day workshop on this years ago. It was like 24 hours, and I felt so dumb by the end. It's awful. Okay, so spectral analysis is just a general way of decomposing time series into constituent frequencies. So Fourier analysis is within the umbrella of spectral analysis, but spectral analysis is more broad. So but it's just a little easier to sort of motivate it with a Fourier example. So here's an example of a spectral analysis where we have a model for X, so T, here's our time series of interest, and we're just going to treat this as a linear regression problem of a bunch of sine and cosine waves. So we've got an intercept out here, and then it just says sum up A1 times this cosine wave plus B1 times the sine wave, and then do that k number of times, however many we have. And if we make this big, again, we can come up with all kinds of funny patterns that are, again, regular, so they will repeat over some number of times. From that equation, we estimate these A and B's. So we have for each of the different waves frequencies, we have an A and a B. And then what we can do is square each of those for like K and plot those against the lag. and we'll get what's called a periodogram or periodogram or parodogram. I've heard it called a periodogram. Anyway, I don't know. Which is similar to the sort of the autocovariance and autocorrelation functions we showed. So there's going to be a response on the right or on the left versus frequency on the right. So the way to do that in R is to this function called spectrum, where you just pass it a vector of values, and then you have to tell it whether you want the log on, off, or in decibels. On is the default. That can make the figures actually kind of hard to interpret. Log can be nice if the data are not too squishy, and decibel is nice for anybody who's actually worked in sound and not like acoustics work, because then that actually means something to you. So here's an example where I've computed the periodogram for our original XT using the decibel scale. So on the left side, the y-axis there is decibels, which in itself is a log scale. And then here are frequencies. And it's a little bit funny because, again, this is in like, this would be per site per unit times, and it is not 0.3. So clearly there's a lot of variation up high. There's a lot of energy here that's going into these very low frequencies. Or I'm sorry, those are high frequencies, because this is 1 over. And then there's not much going on here. These little dips in here are just because we have a repeating cycle. So every once in a while, there's a repetition that looks like that. This error bar, or this mean right here, there's a mean, you can barely see it, plus a confidence interval in these outputs, tells you that most of the observations lie in this band. So if you think about a band, drawing a band across there and why they put it in the upper right instead of over here, that would say that almost nothing is really looking like this. Everything is really looking like this stuff up here, which again makes sense because we didn't use all of these really long waved sine waves. Okay, here now, there's a little code you can find in the RMD. I computed this to be the natural scale, and this is now in actual cycles, so it's a little easier to think about, right? So we have 1, 2, 3, 4, 5 spikes at relatively low frequencies, which makes sense because that's the way we simulated those data. You can estimate the spectral density via an AR model. So it turns out that, you may remember once upon a time we talked about how you can represent MA models as infinite sums of AR models with an error term and vice versa. There's this reaction. You can create a Fourier representation of a model through essentially an infinite ARP process. So if you make P super duper big and estimate that, like fit that to something like the PDO, which has some variation at sort of 3 to 7 years and some at 10 to 15, and then others at sort of 50 to 70, you can simulate a time series based on that will look in spectral form like the original time series. So just overfit a really big AR model, simulate from that, calculate its spectral density. They will statistically be significantly the same. So anyway, let's say you've got an AR model for your data. And once you've estimated all these P's and the observation variance, or the process variance, I should say, of the E's, so you know all of these things now, you can ask for a given frequency, what's the spectral density? In our case, almost always delta T is 1, so these go away. And it's just essentially 1 minus the sum of these AR coefficients, these are all weights less than 1, times this Euler equation here. And this is, I didn't do it in here, but you can sit down and simulate this if you want. It's kind of a fun thing to do. Find something that you know has some really strong signals in it, you did a really high, or like an AR12 or something like that to it, simulate from that, and then fit the spectral densities and look, and especially if you smooth them a little bit, they will all have some similar shape. They won't look like this, but they will have a very characteristic shape. Okay. Limits to spectral analysis. It works really well for stationary time series, so things that don't have big trends. And when I say stationary, we're going to ignore the sigmoidal part of this because that's actually something that they work really well on. That said, they tend to be very inconsistent estimators. They're not well behaved, and some people will say, "Oh yeah, you need like 1 million data points." I've read this before, and even then, they can be really biased. There was something I read once where someone was like, hey, "Everyone, it's been well known this has been a bad idea since 1858." or something like that. Okay. So anyway, from a quick and dirty perspective, if you want to estimate the spectral density using spectrum, it will give you some idea of what's going on, but you'd be better served by using a more rigorous method, something like Fourier or wavelets. Okay. All right, so now we're talking about changes in amplitude with frequency. And in the time domain thing, we've talked about oftentimes changes in amplitude with time, but we don't really think too much about stretching and squishing the time axis, what effect that would have. Like what if just in the middle of the things we started sampling every minute instead of every day, that sort of thing. Well, you can imagine a time series where the frequency changes. So right, we have something where it has a really, and then it starts to get really long over time. Right then, again, in natural systems, those are not so common, but in physical systems, those exist, like when springs wear out, that happens, or those sort of things. A natural example is the rotational velocity momentum of the Earth is not constant, right? So our length of day varies every year by like milliseconds. But if you have the precision to measure that, you can actually see that there's some change. So if you looked at the length of a day, that thing would push-pull. It's not a fixed frequency over time. And there's been some other work in natural time series where people are starting to look at this with respect to like freeze-thaw cycles and lakes and these kind of things. So anyway, frequencies can change over time. When we think that may be a case, we can use what are called wavelets or little waves. And a wavelet is nice because it's a localized function that changes with both time and frequency. And we'll spend some time now talking about what I mean like that. So here's sort of the way I think about this in kind of a graphical schematic. If we had the time domain, so here's our regular time series, the only way we're going to get any information is by marching across here, right? If you just fix time and run this way, there's nothing. It's just a straight line. Here we've been talking about, that's not, I screwed that up. This should be, oh no, this is right. Sorry. Okay, so in the original time series, right, we're not getting any information about the frequencies. In the Fourier transform or frequency analysis, moving across time isn't telling us anything. It's when we step across the frequencies, right? When we pulled that thing away from the board and then look down this direction, that's where we got that information. Wavelets, we're going to get some information about both. So as we move through time, we're going to have this localized thing that kind of marches along with us, and it's going to tell us something about local changes, and then we're going to make the size of the sort of window that it marches across bigger. So it's going to start small and then we'll go bigger. So, right, at first you can imagine breaking the time series into 2 halves, then the fourths, eighths, a geometric progression like that. It gets chopped up. So when you interpret wavelength plots later, there'll be something about the time here and something about the frequency here, and then there's usually some sort of heat map. And it will tell you that, oh, at every time point, there was a really strong signal here every year, or something like that, or every 6 months you could see this, or if there were El Niños, you might see every 5 to 7 years, there'd be a really strong correlation and something like that. Okay, so what exactly is a wavelet? Well, it's a small wave, I just told you that. All a wavelet is a function here of time where you have to specify some scaling factor, sigma, and some time shift tau. And once you do that, you have to pick some sort of scaling functions inside here that when put together are going to yield the right wavelet. That's all very hocus pocus. The two defining things about a wavelet is that it has to go equally up and down. So it is equal density above and beyond. So if you integrate it from minus infinity to infinity, you're going to get 0. It also has a finite sum. So if you integrate it over that entire thing, the magnitude of that has to be less than infinity. So that's really the only two rules to making a wavelet. But making all of this work in the background is more complicated than you might think. Okay, how do you actually assemble these wavelets? So basically, what do you put on the right side of this equation? Well, there are two, whoops, sorry, going the wrong way here. We are going to use what are called scaling functions in the literature. And these are of two types, one that are called dilations. So the idea here is that you want to amplify the signal at some time. And the other one are translations, which just means we want a shift. I just wrote 1 here, but you could imagine this being something, and that could be something other than 2 as well. But the idea is that, do you want to shift this wavelet one direction in space, and do you want to stretch it out depending on its position? More generally, this is the function for a wavelet. So you have 2 to this j over 2 power times some scaling function that's 2 to the jt minus k, where j is going to be your dilation index. So that's just basically going to determine how big this thing gets, how much we want this thing to stretch this way. This little bit out here is just a normalization constant that comes into play. And then k is just the translation index. So how much do you want to shift this thing one way or the other? Okay, so we have a lot of options for those scaling functions, infinite as it would turn out. But we want to come up with a situation, and in general with wavelet analysis, where we've got some scaling functions here that are weighted, and the sum of those will give us our desired wavelet function overall. So these C sub k are called filter coefficients. And so the idea is that if we have a lot of these filter coefficients, so k, capital K here is relatively large, then this wavelet form is going to look relatively smooth. And if we just have a few k's, it's going to be something really blocky. It will be real jagged and short. And the other ones are going to be long, and they're going to go like this.
So are there sine waves and no sine waves involved here, or not at all?
They can be, but that is not a requirement at all. In fact, the first one I'm going to show you is one of the simplest. It doesn't involve any of that, so no trigonometric functions whatsoever. Okay, the Haar wavelet is a well-known and well-studied one in the wavelet literature, and the way that works is k here is going to be 1, so this sum is going to go from k equals 0 to 1. Both C0 and C1 are equal to 1. So the weighting here, this is going to be unity in both cases. So if you put these values into our general equation, that means that our wavelet is going to be formed from these two scaling functions, right? Because when k is 0, this goes away, and that's 1, so it should just be 2t. And when k is 1, you put a 1 in here, that's 1, so it should be 2t minus 1. So the sum of those gives you our wavelet. It turns out that if you do the algebra, here the only way to satisfy this equation is to say that Wt is going to equal 1 if t is in the interval 0 to 1, and otherwise it's 0. So this is going to look like a step function or a wall. It's going to look like a wall. That's a horrible metaphor. There it is right here. So this is Haar scaling function, which is essentially thought of as a father function for whatever reason. In the wavelet literature, they do this. But here it is. It's 0, or the value is 0 until it hits 0, then it jumps to 1, then it comes back down to 1, and it's 0 everywhere else. And you may be thinking to yourself, well, first of all, negative times, this is kind of odd. And we've got an entire time series, so we're just going to look at time 0. Well, the time index here is irrelevant, right? Because you can tell me I measured it in months from 1963 to today, and all I have to do is subtract the mean of 1963 to today, and now the time index is this. And in practice, the way this is the time series you take is like this. You wrap it around a wheel, and then this wavelet runs around the wheel. And it's too hard to explain in graphics how that works. On a whiteboard, it's a little easier, but that's like I said, that's about an entire day's worth of lecture. But that's just in practice the way it is. So this is, you can think of as this is going to be a filter that gets passed through this thing. So this is still our scaling function. We still don't have the wavelet itself. So we know what the wavelet, or we want the scaling function to look like, but we have to express this in terms of dilation and translation. So our dilation equation was psi of 2t, and the translation was psi of 2t minus 1. So again, in order to make this work, it turns out that for this one, it gets 1 if it's between 0 and 1/2. And over here, it's going to get 1 if it's between 1/2 and 1, and be 0 otherwise. So if you put these two together, because remember, we would have to add these two. This was k equals 0, this is k equals 1. You add those two together, and this is what you get. So here's our dilation scaling function. Here's the translation scaling function. If you sum the two of those, you can see that you get that original scaling function we want. So back to your question, Mark. So far, no trigonometric functions needed at all. Now, to go from the scaling function to the wavelet, we need to do a sort of a differencing. And in these discrete forms, that's really easy, especially with HARs, because we can just use this little trick here, where we say -1 raised to a k is going to force this thing to alternate for us. So we're going to get a differencing every time. So when k is 0, this is going to be 1. That gets -1, right? Or I'm sorry, it's raised to a 0. That means this whole thing is 1. When it's 1, it's -1. When it's 2, it's going to be 1. When it's right, it's just going to alternate -1, -1. So that means we have this step function. Now it's going to flip the thing around on us. So that means from that scaling function, the father scaling function, we can get this mother wavelet. So here is HAR's mother wavelet. Cool. Isn't that exciting? I know, it's going to get crazy. Okay, that is the mother wavelet. And we can create children from mothers, once we have them, by just messing around with the dilation and translation aspects of this. So in that first one we fit, j is 0, right? Oh, that's for the scaling function. If we go back a couple, you can see that this ends up dropping out, and this goes away as well. So, oh, because k was 0 as well, right? Because our original wavelet was this times 2e. So now if we make j equal to 1, we get now just one of the daughters, and that daughter wavelet looks like this. So now it's the amplitude out here is not 1, it's a square root of 2, which is about 1.44, something like that, and we still have this other translation and dilation aspect to it. Again, we can just put this differencing operator in here, -1 to a k, and if you do that, you'll come up with this. So this is now the daughter to HAR's mother wavelet, or the first daughter, as it turns out. There are any number of KP, KJ combinations, I should say. So this is it. So you can imagine now, this is a filter that you then are going to run some signal through, right? We might have some EKG, or we could have some output from a muscle. You know, we're trying to measure the jumping power of frogs or something like that. So I know people who do this. That said, that's just one. That is perhaps the simplest, and it's in a nice discrete form, so it's easy to do. There are many, many others. If you just Google wavelet forms. You'll get a whole list of them, many of which have really been developed like in the 70s and 80s. There was a little bit of work done like from Fourier's time, but then it just kind of went dead for a while. And then a bunch of people started picking it up. And I'll say that one of the interesting things about wavelet, they all end up with really strange names. Like there's a Morley wavelet, which is okay, named after Morley, and there's HARS. But then there's this French physicist named Dobschies, and she made them like she had the least asymmetric. I'm like, well, why wouldn't it be like most symmetric? Nobody could give me an answer on that, you know. And then she has one that's just D4. I'm like, well, okay. Anyway, there's so here's some forms. So this is a Morley wavelet, and we're going to see this in practice later. This one is in continuous time, so this is one where it's not a discrete function. It is essentially an exponential and a sine stuck together. So you get this, it looks like a sine here that dampens out on both sides. Here's another one with a really great name, the Mexican hat. I hope everyone can appreciate how it got that name. The zeros got cut off here, but it's somewhere like in here, so that the positive masses or density is the same as the negative density. So all of these would integrate to 1 if we did it over the ones. But anyway, so here's some examples of those. Okay, I seem to be making quite a bit of a deal out of these wavelets and like why anyone would actually do this. Well, there are a number of applications of this, and one that's very, very popular now is for video compression. I think they do it for audio compression as well, right? If you have a digital camera and you take a picture in a raw format with a really nice SLR, that picture is enormous and it has a lot of things. So it's saved or can be saved in a number of formats, like JPEG, for instance. That is just a resampling of the original. That does not have the true image in it. So here is an example of the JPEG 2000 technology. It's a little bright in here, but here is a picture of a sort of a castle or a manor in Europe. And these are sequential band passes through here. So this one right here is a low frequency filter. So it's only picking up the really strong lines of the architecture, right? Like the corners, the edges of the tower. And then as you get through, find down to here, now this is picking up all the little fuzzy details. So by just saving some number of composite images, when these are all stacked back together, you'll get this without saving every little bit of it. So that's a very real world practical application that people are doing all the time now. Okay, how about if you wanted to do this in R, for instance? There are a bunch of packages out there actually that will do this. One of them that I'm familiar with is called this Wavelet comp. It uses a Morley wavelet. The influence of the wavelet itself is not huge because a lot of them have this relatively similar shape where it tends to look for a peak and an impulse response, which the HAR wavelet, I'll back up here. This is a classic one as well in signal processing. Even the one that just is a bump up is a classic. So if you play various sinusoidal waves through a filter like this, you'll get a very known and expected response. So given that, it doesn't, the actual choice of the wavelet is not super important. Okay, so here's that package, wavelet comp. I'm going to do an analysis of the Lake Washington temperature data, which everyone has seen here most of the time. Wavelet comp needs the data as a data frame. It's a little bit peculiar that way. And this is the driver function. Here's this analyze wavelet. In order to do that, it's kind of funny because you have to pass it the name of the data frame and the column name that you're interested in. This lowest span is a sort of pre-massaging that goes on before the wavelet is computed, because typically people are using noisy data. The lowest is basically going to smooth out your data first and then pass that to the wavelet. So if you had really, like some of your data, for instance, Michaela, you could imagine doing a small lowest on that to smooth out a little bit of the wiggliness around there, and it would just help pick out the real important longer frequency waves as opposed to all this short stuff that's this wave. Just set that to 0 if there's no trend. The time step dt. It says, of course, it calls it like frequency, and we talked about this with respect to just like the TS function. Basically, you want this to be fractional. So it's 1/12 if you have monthly, 1/24 if you have hourly data. There is a default for this lower period, which is 2 times this value. And what this lower period is you can think of that window that we're going to have it. So you have a time series. We're going to cut it in half and essentially pass that wavelet through half of it. Then we're going to cut it into fourths, pass it through half of those fourths, then cut it into eighths, pass it through that, et cetera, et cetera. So this is just setting the lower limit to that. And you can't go too low because you'll be inside your sampling interval and it won't do anything anymore. And there's an upper period in here which is fixed as well at like about 1/3 of the maximum length of the time series. Because of that, as soon as you get those things, the windows get to be huge. There's no data to analyze them. So if we were doing in medical profession where we had a probe that was reporting, in milliseconds, then we would have all kinds of data to use. But in our case, we don't. There's a significance that can be assessed, and so it has to do a resampling to do that, sort of a bootstrap exercise. You can tell it how many resamples to do, and I tell it this, but it still will report. So if you run this command, it actually comes up with a really nice little progress bar that shoots across here. But when you knit the slides, this is what it looks like, something like that. And this takes 10 seconds, maybe not even 5, something like that. It's pretty fast. And this is what you get out. So you fit this. So here, I stored this as wavelets estimated, WS, and I just passed that to this wavelet.image function. And that will produce this as is. The default color palette is rainbow, which is not at all colorblind friendly. So I like the Viridis palettes. So here is the period, and this is time. So this is the beginning of the time series, and this is the end. That's why I was saying, so this thing got wrapped around a wheel, and that's how come we could actually do this here, is because we're using some information from over here. And the reason that people do that is they tend to think of this as a sort of a continuous, or a continuous sort of stable, stationary kind of thing, right? So the idea is that whatever this process was, it shouldn't really matter where we sampled it. So bending it around is okay to get, especially because we're trying to pick out these regular cycles. Okay, then this is the power in your spectrum. So down here means there's very low power. So if you think about that spectrogram, these peaks hardly exist. And where it's really dark purple, that's really intense power. And this white bar here is sort of the estimate of the significance. So in this case, it would say that more or less at any time period in our time series, when we have a period of 1 year, we have a lot of power. And that totally makes sense because we're using a temperature data set that has an annual, it's measured monthly, but it's very, like Januaries look like Januaries, right? Februaries look like Februaries, etc. So this is very expected. But then you can also see that there's some in different points in time where there's something at like maybe 6 months, we're starting to look like each other. So this maybe was a particularly warm or particularly cold year. And then here, I don't have the actual year-month combination, so it's hard to tell. And then as you move later, so this would be a thing where sort of 4 years, there were some 4 years that looked a lot like each other. This band right here is a function of the fact that as your periods get older, you're shrinking down. It's like when we did the linear filtering on one of those first days of class, right? If you make that filter really big, you need a whole bunch of stuff before and at the end, so you can't get out here to the end. So that's what this is doing. But all this stuff outside of here is really kind of bogus. So there's your wavelet spectrum. And you'll see in papers now, this will pop up all the time in the ecology literature because people are starting to do wavelets more often. Typically what they'll do is they want to get the anomalies from here, and they'll look at things like high flow events or low flow events relative to some sort of regular pattern. Okay, let's say, like in the Fourier case, once we had those transforms, we wanted a way to come back and recapture sort of its estimate of our original data. Well, wavelet analysis, we do that as well. It's just that it's really hard. You have to integrate over both of the sort of parameter vectors of weights, the A's and the B's. And this is not easy to do, so there's a bunch of software that will do it for you. And the solution to this usually involves a sort of like a decision tree type thing where it starts finding out who's similar, who's not, who's similar, who's not, who's similar, who's not. And where those breakpoints are those periods. So it starts to, and it will iterate and iterate and iterate and iterate. And of course, nowadays it can do this really quickly because we have really nice silicon. Okay, so if you pass our estimate to this reconstruct function, it will draw a plot of your original data in black and in red, the sort of estimate based on the wavelet decomposition. So it's not perfect, but it's really pretty good in general. And again, this has a really fairly strong seasonal pattern. I probably can poke around a little bit and look for one that's where you actually see some shifts, something like PDO, or something like that. It's a little more interesting because you get some high autocorrelation, but then there's these things that show up at longer and longer periods, and that changes as you move along. So anyway, that's it for wavelets and frequency domain. Like I said, in fisheries and ecology, you don't see a lot of this historically. So now it's starting to come up a little bit more because people are actually starting to generate longer and longer time series. But at least now, hopefully, if you're reading a paper and someone said something like, "Oh, we did wavelet analysis," you have at least some understanding of what that is. Or if they show you, like I said, because these types of figures show up all the time now.
They're beautiful.
Yeah, they're usually pretty, right? Yeah, it's sunset on Hawaii. Or it's like the first level of hell. I don't know. Okay, any questions?
What are the white lines in that?
These white lines?
Yes.
This is sort of, it's a significance level. Remember there was a resampling in there that would tell you, so that anything inside here is sort of significantly the same and has sort of significantly high power, that it's not just background junk. And you will see that sometimes it's not always this way. Like you might get one where there would be a white circle around some points here or something over here. Yeah.
When wavelets can be used for non-stationary frequencies of periods, whereas Fourier and spectral analyses are stationary.
Yeah, people have done Fourier on non-state, like things with trends, but oftentimes they remove the trends first because it's not so much, the trend isn't so much what people are interested in. It's more around like, yes, what do we see,
But like changing periods, like those seasonal signals, you would get like this.
That's right. You can do it. Like if you passed it a time series that had, like it was that stretch spring I talked about, and estimated it, it will spit back something to you, but the reconstruction may not actually be very good because it'll get, when it's varying with high frequency, it'll get that part right, and then when it's over here and it's varying with low frequency, it'll get that part right. And then there's I thought I had put a link to it in here, but I didn't. But I found the prof who did a wavelet analysis of someone saying, "I love wavelets." And so so you have a sound intensity over time, and you pick up with I love wavelets, something like that. And then you recover the power spectrum, and you can see where they, where obviously they're hitting the hard consonants, you get these kind of pulses, but then there's spots in between where there's just nothing. So, and that's one of those things where it does look like that, depending on how high we're talking, right? The thing will speak up like that, and then there's nothing for a while. So yeah, you can see some of these time series that are really bizarre, like earthquake sensors, right? Where they have things just sitting there wiggling around background because the plates are just kind of grinding together on occasion, and something really jars and it goes up, and then things will settle back down, and then we get closer to the sun and something changes a little bit more. Yeah, tides is another one where it's not a perfect, right? It's not a perfect 12-hour cycle on tides, so that the frequency is actually changing.
So where are people using this in? ecology or fisheries?
The most recent example I've seen it is, Albert and John Sabo.
Yeah.
There's some people, well, Albert's at Berkeley now, but John Sabo's at Arizona State. He does a lot of work in intermittent streams and stream ecology in general. And they're interested in sort of the comparing and contrasting really high flow years or situations to really low flow years compared to sort of baseline areas, and they're working like in the desert Southwest, right? So sometimes these streams are just dry for most of the year, and then some monsoon comes through and just blows them out. So, but they have a typical rainfall pattern that then can classify with some wavelet analysis, and then you can get from the reconstruction here, they take the difference. So the big outliers will show up in the reconstruction.
Transformations for that, because I might use it for my project too.
Oh, well, I know that for some of them, I know they're using wavelets, but they probably did. Yeah, I know, because Tamara just sent me something on another one that we did for an example for a paper we're working on. Anyway, but it's the same idea. If we had done this with Fourier, we could have got the same thing, right? I mean, the one I was doing before was a totally deterministic signal, so it picked it up. But yeah, then you would just look at the deviations. It's not radically different than if we just fit, a Mars type model where we had a fixed effect for a month or something like that, and then we got this kind of thing. We just picked off the residuals from that. Yeah, I think it's probably a way to obfuscate the reviewers and make it look as though you're really smart.
But you could do something where you had kind of a more funkier cycle, where it wasn't this, strictly one peak, like what you were showing in the very beginning.
Yeah, exactly right. Where there's times where you might get, like in freshwater lakes, there'll be a big pulse of production not long after ice out when all the diatoms come in. Then they become silica limited. They all crash. So if you look at that, there can be double peaks, and one can be higher than the other and stuff. Yeah, so you can get more or less regular series that still have a bunch of wiggle around them that, yes, it's not, for some reason, because it's, you can imagine some combination of temperature, light, and fertilizer causing differences depending on what time, for a given. Fix two of those and vary one, and you'll still get.
So will the Fourier transform deal with cases where, like, you have your frequency changing? Seems like it wouldn't.
No, not well. That's basically what Lily's getting at. Yeah, it's just going to pick out. Yeah, it can deal with the fact that these are all out of phase, right? But the actual frequency is not changing. So yeah, if this one that has this really long wavelength here, if that one was sort of an elastic stretch, so it was really stiff material down here, and then once it got out here, it got really, no, it wouldn't work well at all. It becomes confusing to it because it can't see that they're, right? Because it's working with the sum. And at some point, then the sum doesn't look as normal as it should. It starts to look kind of weird. Yeah. You can simulate it and do it. It's actually, pretty informative, because at some point you can totally break it. That's not true. Yeah.
Do you usually have to smooth these things like less before?
That's a good question, Mark. I don't have a definitive answer to that. For this example with the temperature data, I said no. I guess I didn't plot the right, because they're not that wiggly around here. But if you were looking for this really strong seasonal, and instead these temperatures were made like every minute or something, so there's all this kind of funny zzz around there, then that you may want to. The whole point of the smoothing is so that you're not picking up a whole bunch of, down, it's rows here. This is all the high frequency stuff down here. And see right now it's picking up some of this right there. It's gonna start to pick up on the correlations and the noise. So it'll pick up spurious wiggles. It's like, oh, this wiggles every day. Yeah, because we sampled every day. Sensory. Yeah.
Phase,
Well, it's because in this case, right, this thing does this low S for you in the background. So some people will just, they'll pass some filter through the data initially with the expectation being like, I'm not interested in anything below this frequency anyway. So just, But like I said, I mean, the literature on this stuff is enormous. The short course I took was from a guy, Don Percival, who's in the applied physics lab here at UW. He literally there's a book that he's written with another guy. It's a big fat thing. They had a MATLAB package for a long time that I think now they've done in R. There are lots of books, the papers,
Does he teach time series in that department as well?
He might on occasion. That has moved around from, when I took it, I taught Tillman Knighting was the person, but he does more spatial stuff than time series thing. I think at the time he was low person on the totem pole, and so, hey, you're a new prof. Guess what you're going to teach? Yeah. Okay, let me just stop this then. I'm done.